My name is Rebecca Medlin. I am a member of the research staff at the Institute for Defense Analyses and one of the 2020 workshop organizers. For those who are joining us for the first time, DATAWorks is a workshop that we've designed to build a community around rigorous statistical approaches to solving complex problems that we face in the DoD, NASA, and the national labs. The organizing of this event has been a joint effort between IDA, DOT&E, NASA, and the American Statistical Association's section on statistics in defense and national security. Before I introduce our speakers for today, just a few things up front. All of their materials that they'll be sharing with you are available right now on the DATAWorks website. If you look in the webinar agenda and today's announcement, you'll find a section with the materials, so feel free to download those. With that, I'm going to kick off today's session, which is on the topic of statistical engineering. We have 3 speakers who are going to give excellent talks. Our first speaker is Geoff Vining. He is currently a professor of statistics at Virginia Tech. And among his many involvements and recognitions, he is the founding and current past chair of the International Statistical Engineering Association, so a topic that he'll be sharing with us today. Dr. Vining is the author of 3 textbooks and is internationally recognized in the use of experimental design for quality, productivity, and reliability improvement, as well as in the area of statistical process control. Dr. Vining has done extensive consulting with the Department of Defense and NASA, and many of his PhD students, including myself, have gone on to have very successful careers supporting the Department of Defense and NASA. So Dr. Vining, with that, I am going to turn it over to you. I'll stop sharing my screen and give you control.
Are we there?
Yes, we can see your first slide.
And you can hear me. This is a miracle. So, Rebecca, thank you for that introduction. I never know what to do with formal introductions. My job is to introduce the overall session. So what I want to do is provide a big picture and give a context for statistical engineering. Adam will be speaking from his experience at NIST. He's got a really nice example, and he does a very nice illustration of the various phases to a statistical engineering project. So I highly recommend it. And Jim has been so involved with the DoD for so many years. He's doing his talk is a very outstanding job, showing the applicability of what we're doing in statistical engineering to DoD opportunities. And he does a very nice job of integrating tools within the statistical engineering framework. So that's the theme. That's what we're trying to do with this session today. So the outline for my specific talk, I want to give us the big picture and understand that the roots of statistical engineering are scientific method and systems and statistical thinking. I want to make sure we understand the basic phases to a statistical engineering project that will help put both Adam and Jim's talk in perspective. I want to talk about core processes and overarching competencies that'll make more sense as I get into the talk. And if I have time, I want to relay some of the experiences I've had teaching the very first course in statistical engineering this semester. And it's not simple to teach complex opportunities and their solutions to undergraduate and graduate students. And it's been an exciting and humbling experience. So I hope I have some time to talk about that. And then I'll conclude with some of the enduring value of what we're trying to do with statistical engineering. So the big picture, when we're dealing with these major opportunities, they're always unstructured and they're a mess. Generally, they're quite large and they got to have data for their solution. The project that my students are working on is trying to help the governor of Maryland make decisions for allocating the resources he's gotten from the federal government in the best way possible within the state. That's unstructured, it's a mess, it's large, it needs data. It sounds like a lot of the problems that many of you deal with on a frequent basis in the DoD, in NASA, and at the national labs. Secrets to success, you got to have the right subject matter expertise for the specific problem. Analysts cannot solve these complex opportunities by themselves. Really have to understand the first principles, but you also have to have the analytics to support that. So the key is to have the right tool sets in the room, both in terms of the subject matter expertise, but also in terms of how to do the analytics, but also in terms of how to collaborate and work as a group. And you also have to think strategically, and once you've got a basic strategy in place, you've got to roll the tactics out in an appropriate manner. These are things we're not taught in graduate school, and that's the reason why statistical engineering is very exciting for us today. So the basic foundation of statistical engineering, statistical scientific method, I want to make sure we appreciate that. I think most people in this call do understand that. Systems thinking. The approach has to be structured but not rigid. One of the criticisms of Six Sigma was that it was extremely bureaucratic and extremely rigid. The goal of statistical engineering is adapt and overcome. Whenever you're dealing with a complex problem, your original strategy probably is going to have some shortcomings. You're going to have to go back and revisit it, adapt and overcome, and ultimately learn from the journey. We've got to capture the essential elements of the successes and the failures of our project so that we can teach others what worked well, what did not. And I cannot emphasize that last component enough. That's where we're missing. We don't have enough case studies. We don't have enough stories to share. And that's where we're going to bring out the best insights of how to attack complex problems and opportunities. So what's the scientific method? It's ultimately a sequential learning strategy. I mean, Box hit this right on the head. You know, Box would always begin just about every class, every course with, here's the scientific method. And there's a reason why he would do that. You got to start with what's the real problem? If you don't understand the real problem, you have no chance to come up with a solution, not an appropriate one. Once you understand it, you got to define it. You've got to provide some structure to it. You've got to explore and discover solutions. You develop a theory to explain why the solutions work. You test the theory using data, you modify, and you iterate. It's sequential learning. But it also requires proper analytics to support subject matter insights, hence the strong need for interdisciplinary collaboration. Data are the keys to this. Don Marquardt, I'm sure he is the last person who will ever be president of the American Statistical Association who did not have a PhD. But he had the experience, the insights. He published like a PhD. He was in charge of the applied statisticians at DuPont. And he said in his ASA presidential address that industrial statistics, quality engineering is the handmaiden to the scientific method. Why? Well, the key to the scientific method is determining what data you should collect, having a proper data collection method, analyzing it correctly, and understand how to interpret it. My God, that sounds like what we do. So that's important. Statistics is critical to this. Subject matter insights, of course, have to guide everything. I remember the first NASA problem I ever had to deal with. There were problems of shorting out of batteries in the mid-90s that were intended for the International Space Station. Now, I'm trained as a chemical engineer, and the one thing that I hated was electrochemistry. Guess what kind of problem I was dealing with? Electrochemistry. I had a engineer from Glenn at NASA tell me, God, Geoff, you could be a hero to your country if you solve this problem. And I said to myself, I was smart enough not to say it out loud, you idiot, I can't solve this thing. I don't know anything about electrochemistry. But I can work with an electrochemist to plan an efficient and effective experiment, analyze it, and solve the problem. So it's important to keep that in mind as we do these things. And this interaction between subject matter insights and analytics are essential for solving the problems we're talking about. Strategy for success. We've got to identify the right tool for the right job at the right time and correctly apply it. There's no rocket science here, but it does mean that you have to have a broad tool set. You have to understand what those tools are really effective for solving and what they are not. You've got to understand what is the right time to bring that tool in, and you got to correctly apply it. Too often, particularly in the analytics world, everybody's got their hammer. It's a different hammer, but they're all looking for nails. But sometimes the problem needs a screw. And that's the reason why it's important to understand a broad set of tools, identify when the tool is correct for the specific job, understand when to apply it, and do so correctly. Tools are not the focus of statistical engineering. We've been asked many, many times, how is this different from data science? Data science is an important component of statistical engineering, but statistical engineering is a strategic and tactical application of data science, along with organizational psychology, along with basic first principles science. The goal of statistical engineering, the goal for any solution to a complex problem, is a sustainable solution. That's what our focus is, how to create solutions that will last for an indefinite period of time. Box, I always like to talk about the second law of thermodynamics. Sooner or later, all processes degrade, but you would like to have a sustainable solution such that you can postpone that as long as possible. Point, tools are not solutions. I like this schematic. It's me as a very poor PowerPoint engineer, but I like to think of statistical engineering in terms of the people and the tool sets. In the center, statistical engineering is the strategy and the tactics, and its goal is the box, better, faster solutions to complex problems. But how do you do that? Well, you got to have the right people in the room. So the true subject matter experts from the critical disciplines for this problem. You got to build the team. And you got to be able to collaborate. Collaboration is essential for success. What are the tool sets? The tool sets from the subject matter expert, critical for everything we're doing, but it's data science, statistics, business analytics, whatever you want to call it. It's industrial and systems engineering, operations research, management science, modeling and simulation. And we see some of that today, particularly in Jim Simpson's talk. And it's understanding how to the organizational behavioral psychology to get the most that you can out of the team. That's much more than any one of those individual components. Statistical engineering is how do we put that all together to come up with better, faster solutions. So what are the phases of statistical engineering? First step is somebody's dumped a mess on you, okay? Coronavirus is a mess. Now, that's a problem. Now, in the particular case that my students are working on, how do we help the governor of Maryland allocate resources to mitigate the impact of the virus in his state? Well, the first thing we got to do is provide some structure to the problem. Okay, so identify what the real problem is, provide structure, understand its context. And context is as broad as can be. You got to understand the science, you got to understand the business, you got to understand the personnel, you got to understand the politics, all of that, none of which were taught in school. But this is the first beginnings for how you can begin to structure the problem and get it into a form where you understand how to develop a strategy to approach it. And you have to iterate 1 through 3 as necessary. Once you've got those first 3 steps pretty well down, you can develop a solution strategy. Now, we're not talking about the tactics yet, and we're certainly not talking about the tool sets yet. We're talking about here's the problem as we understand it. Now, how do we come about to, how will we achieve the solution? What is success? These are all parts of the solution strategy. Again, we're trying to stay above the problem, understand the problem, and then attack the problem. Once we have our solution strategy, it's pretty straightforward to develop and execute the tactics. Most analysts are very familiar with step 5. That's where most of the data science really occurs. It's steps 1 through 4 that help lay the foundations for success. And then ultimately, we've got to deploy the final solution. Now, as I have said, as we get into the problems, you have to iterate between 4 and 5. The initial solution strategy may run into an issue. Failures are important. One of the things that you learn in innovation, don't fear failure. Fail early, fail often, but learn. Make the call early, not late. Investigate it thoroughly. Learn and document. And if that means you have to change your solution strategy, that's fine. That's fine. That's the adapt and overcome that I talked about before. After it's all done, document it. Now, for many of you, the final documentation will be proprietary, cannot be shared outside your organization. I got that. But make sure that it is documented and make sure that it's shared within your organization. Emphasize, what did you learn? What worked well? What did not? What are your recommendations for next time? So that then you can guide people to be more efficient and effective down the road. Even if it's proprietary, almost all organizations have avenues to publish that final document for use within that organization. It's even better if you can get it past the lawyers and publish it in the public domain. I understand the challenges there, but nonetheless, that's how we can move the profession further and faster. The core processes, the model of statistical engineering is chemical engineering. And in chemical engineering, you have unit processes, which you can subdivide a chemical process into those specific unit operations. For us in statistical engineering, we call them core processes. They're things like data acquisition. And that's not just planning an experiment. That's actually going into the equipment to actually physically collect the data. It's dealing with the sensors. It's dealing with the frequency of collecting data. So that's the broadest sense of data acquisition. It's not just sampling, it's not DOE, it's both the engineering, the science, and the analytics. Data exploration, playing with the data. You know, a lot of the analytics that I see are wonderful exploratory data analysis tools, and they are critical at this kind of phase. And in many cases, they're wonderful solutions. I got that. But once you have the data, you've got to explore it, and particularly to clean it, because bad data leads to bad decisions. We're living with that right now with the virus. There are no good data on the virus. We're making do with the best explanations we can from very flawed data. It'll probably only be in a few more months that we begin to call out from the current data, better data that can give us even better insights how to attack this problem. What we're dealing with the virus right now is a classic example of a complex problem where the data themselves are not even clean enough for a really sound modeling and analysis, yet we're trying to do that. The next big core process would be modeling. That could be the traditional statistical methodologies, as we've been teaching for decades in the statistics curriculum. Also, it could be modern analytics, the big data. And I certainly emphasize modeling and simulation because that's essential. And that's something I know I was not taught in graduate school. Inference to the process and problem. What kind of judgments can we take from the data to guide us for understanding the process, the problem, and especially in light of how to develop appropriate solutions? We then have to have proper evaluation of the tentative solutions, deploy them, see if they're sustainable. If they are, success. Life is good. Those are the core processes. There are some overarching competencies, data visualization techniques, optimization runs through most of this. Project management, oh my God. You know, that's one of the big developments that Six Sigma brought to the table was the emphasis on how you run a project. Too few of us are taught that in graduate school. Some of the IEs are learning how to do teamwork, work together as a group, and then understanding organizational culture, because that's where the politics is. And if you don't understand the politics, you're not going to get a final sustainable solution through to completion. So I've got a few minutes here. Let me talk a little bit about my experiences teaching it. This is the first time it's been taught really anywhere. Diego Conan in Switzerland has done some things that are similar, but not quite what we're doing. 8 students in this class. They're both undergraduate and graduate. Notice not a lot of statisticians and a lot of industrial engineers. And frankly, I think that's what we're going to see. I expect that there are a lot more engineers and people who are from science backgrounds on this webinar than there are true stats. Amen, it should be. Fascinating. 2 of the students are from Argentina. Virginia Tech required us to go online after spring break. This team has been heavily engaged with the client from just after spring break. We have a true international team on this. Only one of the people was born in the US, and only one had some experience in working in teams, and that was an undergraduate. The syllabus, you know, I was going to teach the big picture of statistical engineering, introduction to team building, and we got that one done really well. We were into the overview and details of the phases when disaster hit the virus, okay? So I never really got to talk a whole lot about the core processes or the overarching competencies. The goal of the course was student-proposed projects, multiple projects, to illustrate each of these aspects of the course. Well, as I said, the virus threw all of that out the window. We were in the midst of defining our first major project. So the first major project the team had to identify were to define their parameters for a major project. And the only comment I had to them was it had to be sufficiently complex and it had to have meaningful progress by the end of the term. So we were doing this 2 weeks before spring break. This was my opportunity to introduce collaboration and how to bring structure to an opportunity/problem. Also, it was to introduce the soft tools like nominal group technique, affinity diagrams, multi-voting, fishbone diagrams, things these students had never really seen before. But very important as we tried to come up with a project, much less a project charter. I wanted it to be their project. They owned it because that would be the most meaningful experience they could have. That was the goal. So we went through that, and then once they came up with what they considered the parameters for the project, then the second major project was to identify an appropriate project. You know, here it is you've defined parameters. Now go out and find something you want to do that we have some chance for meaningful success by the end of the term. It was their chance to apply within their own group the soft tools that I had taught them in the first major project. It also introduced notions like environmental scans, gap analysis, and project charters, which was the real objective of the second major project. Ultimately, identify a project and come up with a project charter to guide your strategy, and that then would guide your tactics for solution. In the second major project, which they completed just before spring break, they learned the art of compromise. The identified project was to try to work with Blacksburg Transit to improve how they deliver their services within Blacksburg. And again, the time was just before spring break. They wrote a beautiful email that I was trying to share with the leadership of Blacksburg Transit. I sent an email to my contact there and I got ghosted, but that's because the governor was shutting down we were shutting down the university at the time. Of course, the governor shut down Virginia soon thereafter. Now, the basic foundations of statistical engineering is all of these things. I talked about them before. Number 4, adapt or calm. Oh my God, structured but not rigid approach. You know, if I had stuck with the original syllabus, we were dead. We really got to experience how do you adapt, how do you overcome. And I am so proud with this group. It's very humbling to watch what they have done. Our third major project, there's a nonprofit organization that was founded by Virginia Tech graduates called Socially Determined, headquartered in DC. So we did a lot with Maryland, with Virginia, with the federal government. Its intent is to use analytics to support policy decisions. It's really very much about the analytics. Our specific project is to support the process to advise the governor of Maryland. How can he optimally mitigate the effects of COVID impact with the federal funding he's receiving? And of course, what we have to do is consider the full effects of the virus on Maryland, on the state. We've got a complex problem here. More importantly, the class really liked this because it was a chance to contribute to a major societal problem we're facing today. Weekly Zoom interactions with the client. The goals really provide new ideas on the structure of the problem that Socially Determined has not ever seen, haven't even thought of. Find new data sources, suggest new indices of virus impact, develop an interesting database as proof of concept, and time permitting, do an initial analysis of the database. First 4, we are presenting to the client this afternoon at the top of the hour. So I can't be here for the whole session, but I will be facilitating a conversation. It's near the end of the semester, and we've got to give to the client the final project. So we're hoping to be able to do some analysis, but at this point, it's more data visualization, proof of concept. Reflection on the original plan. We were successful because the students learned early how to collaborate as a team. This would have been disaster if we had to deal with the virus from day one in the class. I never would have been able to pull it off. They adapted well to remote meetings. As I said, 2 of the members are in Argentina. Each week when we meet with a client, one of the students is the team lead and is leading that meeting. The 2 members from Argentina are undergraduates, and both of them have led meetings with the client. Very, very impressed with them. One of them was a Fulbright scholar. We've had enthusiastic participation of the client, and Fred Fulton has been absolutely invaluable in this whole process. Fred is the one who had the connection with Socially Determined. He was in charge of the operations research group at GE Research in the 90s. He stepped out on his own as a consultant. Great experience with these problems. He's been co-teaching the class with me. It's been outstanding. And it really is an example of adapt and overcome, which I think is a critical element of statistical engineering. And it's been a far better student experience than I ever could have created at the beginning. There's a journey to solving these problems, and it's a well-defined roadmap. And that's our goal in statistical engineering, is to highlight that. Now, there's a roadmap, but each journey is unique. So I've been trying to share with my students. But success requires the same elements: teamwork, collaboration, the right blend of skills. You got to have the right subject matter experts in the room, understand the tools and their roles, understand how to deploy them. You got to learn leadership. And my God, my class, I have seen 3 or 4 of them really develop as leaders. As I said, it's humbling and it's exciting to watch. What's the enduring value of statistical engineering? Well, success requires us to bring value to organizations, addressing really the opportunities that keep CEOs awake at night. That's an opportunity to provide great value. Where it's the current state, there's a focus on a limited number of tools. The opportunity for statistical engineering, how do we use these tools most effectively? And that's what we're trying to do. The future is a journey, and that's what we've tried to do. So here's the advertising slide, and this is my last slide. So I thank you for your attention. We started a few minutes late. Rebecca, if there's time for chat or questions, I'm happy to do that. You're in charge. I just wanted to make sure I didn't cut too much into Adam and Jim's time.
No, this was perfect. I did receive 2 questions, so if you don't mind, I will ask those on behalf of those who asked them. So the first question was wondering if you used a particular textbook to teach your course, and if you have teaching notes that you'd be able to share, or what references basically would you recommend for somebody who wants to implement a course like this?
We're in the process of developing those materials. The best suggestion I have is go to the ISEA website. One of the goals of the handbook, the Statistical Engineering Handbook, is to provide an initial textbook for a class like this. We're in the process of developing that. If you will send me your email, I'll give you access to the Canvas site that we've been using. So I was using a lot of materials from the ISEA website, some presentations that I have made to give some structure to the students, to give them some foundation. But once you get to the website, you're going to see that after spring break, the only thing that you're going to see are recordings of our class sessions, which is where we're discussing the problem. So is there a textbook? No. Do we hope to create materials in the near future? Yes. And, you know, as I said, I'm very happy to give you access to my Canvas site, and you can join us in trying to come up with a better way of presenting and teaching this material. It's a challenge, and we're learning how to do it. It's a complex problem in itself.
And then there was one other question from Christine Anderson-Cook. Her question is, why do you think that so few statisticians signed up for the first course? It seems like that would be something natural for statisticians to want to join.
Great question. Dealing with the students we have here at Virginia Tech, they're all swept up with analytics right now, and they don't see this as contributing to analytics. Whereas the industrial engineers have to deal with real complex problems. So it's a frustration to me, because I was expecting to be able to get quite a few statisticians involved. The plan is to offer this course again next spring. I will be teaching it. I'm hoping we can market it better, but it's just right now, working on these kind of problems is not sexy to the statisticians, but it's extremely sexy to the engineers. And in fact, I think the next big opportunity we will have on the Virginia Tech campus will be in aerospace and mechanical engineering. I'm working with the group that's trying to support Rolls-Royce's Virginia Tech Center for Excellence, and they're really prime to engage in statistical engineering, much more than my statistics colleagues. It's frustrating, it's disappointing, it's reality, and I'm sorry it is.
I think that's all the questions that we have. Just a general comment. It sounds like we might need to bring your class back to give us a talk on their COVID project.
It would be very thrilled to do so. We identified early one of the goals of the class was to write a paper to get published in some journal like Quality Engineering. And there's strong interest in doing that. Of course, we'll have to do that over the summer. So we could definitely, if y'all are interested, I'm sure they would be very happy to make such a presentation.
Great. Well, we'll let you get to that class. And I think right now we'll switch over to Adam's presentation. So Adam, feel free to share your slides. I'll give you a quick introduction. For the community, Adam is a mathematical statistician currently working at the National Institute of Standards and Technology, where he applies statistical methods and thinking to a diverse application areas, including physics, chemistry, biology, engineering, and more recently social science. And Adam has his PhD in statistics from Iowa State University. So Adam, I will turn it over to you.
Thank you, Rebecca, very much for the introduction. And thank you, Geoff, as well for introducing statistical engineering. I'm going to continue with that theme, as Geoff mentioned. And I'm also going to try to turn my video on. So if the video seems to be interfering with the quality of the presentation, I'd appreciate it if someone would send a chat, or Rebecca, if you would cut in and let me know. I like to speak with my hands sometime and be a little animated, so we're going to try video here. All right, so as Geoff mentioned earlier, the primary focus of my talk is going to be the 6 phases of statistical engineering, but using a project that I've been working on for a number of years, the service life prediction of polymers, for context. And what I'm going to highlight, or the thing that I hope to highlight, is this repetition, the loop between the last 3 phases: strategy, tactics, and deployment. Again, something that Geoff mentioned in his talk. Seem to be having difficulty. There we go. Before continuing, however, I have to acknowledge a very long list of collaborators on the Service Life Prediction for Polymers project. This is a very long-running project with a lot of people, as you can see, contributing to it. I have not been involved from the very beginning, so I apologize if I've left someone off of this list. I want to identify 2 people in particular: Chris White and Jim Philbin, who I've worked very closely on this project with. And some of you may know Jim Philbin, who's been a long-standing member of the Statistical Engineering Division at NIST, and has focused a lot of efforts over the years on design of experiments. Another thing that I want to point about this list of collaborators is that you will see that almost all of them, with the exception of Jim Philbin and myself, are subject matter experts. So that's something that Geoff mentioned that is of critical importance to statistical engineering projects, is subject matter expertise. And in fact, the statistical expertise on this project is in the minority relative to the subject matter expertise in terms of number of people on the project. All right. So just an outline before we begin. I'm going to primarily talk about the phases of statistical engineering, emphasizing that you don't start at 1 and end at 6, and the project is necessarily done at that point. I also want to say that I haven't been in the first 3 phases. As you remember, I said on the last slide, I didn't start when this project was initially begun. So I haven't had a lot of direct involvement with the first 3 phases, but I am going to talk about them. But the focus will be the last 3 phases of statistical engineering, where I have had direct involvement, that is with developing strategy, carrying out tactics, and deploying the solution. So the first phase, as Geoff said, was identifying the problem. And on this slide, I can actually kill two birds with one stone, because I can identify the problem for you and describe what service life prediction is to me at the same time. Now, you have to keep in mind here that I actually had the benefit of hindsight, because I was not involved in the initial phases of identifying what the problem was. What is the goal of the project? Instead, Chris White was actually explaining to me what their project was all about and where they were going with it. So can describe what service life prediction is in the pictures on the bottom of this slide, moving from left to right. So on the left, the NIST solar sphere is pictured, and this is used to artificially weather polymer samples, and it can weather samples under precisely measured or controlled conditions of temperature, humidity, mechanical strain, and of course for polymers, one important one is UV exposure. Now let me explain what mechanical strain is before moving on. I think everyone else is probably familiar with temperature, humidity, and UV exposure, but mechanical strain is putting the samples under physical either stretching or compression. And this, especially for sealants, can have a large impact on degradation. Okay, so in the picture in the middle is a picture of a sample of sealant that has already been weathered on the solar sphere, and you can see some noticeable cracking on the exterior. The right picture is an outdoor tester. So this is in Florida right now, and primarily what you're seeing in the picture is instrumentation to measure the conditions that samples are experiencing while they're being weathered outdoors. The goal is to weather samples on the solar sphere, make measurements of degradation for those samples, use those measurements to predict how much degradation is going to occur to the samples that are being weathered outdoors. So before moving on to describing phase 2 or expanding upon phase 2, why do I consider this statistical engineering? Well, it meets, in my opinion, the 3 criteria. It's large. I have a couple numbers on the screen there to try to convince you that it's large, but I think most people would agree that commercial polymers, things like plastics, are a very big business. It's unstructured. In the beginning, there wasn't even at the outset of the project, decisions had to be made about, do we attempt to tackle all polymers? Can we solve this problem for all polymers at the same time? Or do we have to pick them off piece by piece, one by one? That in itself means that which polymers you attack influence things like how do you measure degradation, or how do you accelerate weathering? It's complex, and the complexity stems mostly from the diversity in the polymers there are, and more specifically, the diversity of uses for polymers. So for example, some polymers we wish to last for a long time. We hope that when we put sealant in building joints, it stays there for a very long time and keeps the rain out. However, for polyethylene, that's one thing that one use for polyethylene is plastic trash bags. We would actually like them to degrade very quickly after their initial use, obviously. So the second phase of statistical engineering is providing structure to the process. So you have a problem. Geoff used the terminology a mess. And so there needs to be some structure put in place. This slide represents my own conjecture on how we might put structure to the problem. Again, because when the project was initially being considered, I was not part of this phase. So what I have on this slide is the application of the SIPOC model, supplier, input, process, output, customer, that's described in the Statistical Engineering Handbook, among other places. So what we have is industry partners, as well as NIST, provide input into the research process, raw material, samples of polymers, as well as testing equipment. At a very high level, we can describe the process, how we're going to go about this is weather samples on the solar sphere, weather samples outdoors, make predictions based on what we've observed in the solar sphere experiments, and compare the two. Compare predictions to measured degradation outdoors. The outputs of this project, and this is something to keep in mind, this might be slightly different than if you were to apply statistical engineering in an industrial setting. The outputs are primarily going to be the research results. And these research results are going to be disseminated in two primary ways. Technology transfer, if you're actually designing a mechanical system, or publications and presentations, as well accompanied by adoption of testing procedures in standards. The customers of these outputs are going to be the same industry partners that provided the inputs. They would plan to adopt these new procedures in their development cycle for new materials. The third phase is understanding context. And this is a part that I have played very little part in, but I've talked to Chris, who's played a major part in understanding the context of this. Now, as I mentioned on the previous slide, some of the outputs for this project are going to be new testing procedures and new testing equipment. Now, at NIST, we'll build one-off custom testing equipment, but we will not commercially manufacture the testing equipment. So one thing Chris has worked on is finding companies willing to commercially produce new testing equipment whenever there are industry partners, so polymer producers that need that equipment to implement new testing procedures. Another product, another output, are the new testing procedures themselves, and these need to be adopted into testing standards, which itself are governed by standards committees, and then standards committees are at least potentially comprised of people, and again, who have potentially competing interests. For example, one participant in one of these standards committees could be someone representing companies making testing equipment for current testing procedures. And the preference there with that interest may be to keep the status quo, for example. The fourth phase is developing a strategy. After you provide structure, develop a strategy to solve the problem. Now, what I have here is the current refinement of the strategy. During my time in this project, we have made some slight refinements to it. I won't discuss too many of those refinements, but this is currently the strategy we've laid out. The first step is to identify a degradation metric. How are we going to quantify degradation? And this changes from material to material. For example, some materials have destructive degradation metrics, others have non-destructive degradation metrics. Polyethylene, remember one use of polyethylene, among others, is trash bags. A measure of degradation for that is when you pull on it, how much does it elongate before it actually breaks? For the sealants we've worked on, we've typically used a non-destructive metric, and that is when you pull it just a little bit, how close back to its normal shape does it get? Does it go all the way back to its original shape, or does it stay deformed a little bit? or does it stay completely deformed? The second step is to identify the factors which will influence this degradation. For polymers, those factors are typically things like temperature, humidity, UV exposure, of course, and as well as mechanical strain. That may be the least intuitive one to those in the audience, but remember I said mechanical strain is physically putting the sample under either tension by stretching it or compression. Now, the third and fourth step kind of occur together. The third and fourth are designing a laboratory experiment. So how are we going to weather samples artificially on the sphere? And at the same time, what is our strategy for obtaining degradation using outdoor weathering samples outdoor? Fifth, we'll use a statistical model like a regression model as the basis for predicting how much degradation is going to occur for the samples weathered outdoors. And then the final step is to validate the predictions or just compare the predictions to what is actually observed outdoors. The fifth phase is to develop tactics, and this is the one that I have been most actively involved in. And let's see. I'm going to save some of the tactics for the following slides because that's going to be going to finish up the discussion. Just, I guess, saying a couple of things. Oh, yeah. So my colleague Jim Philibin has been, while I've been primarily involved in the modeling efforts and prediction of what's expected for outdoor degradation, my colleague Jim Philibin has been involved more in designing experiments for the solar sphere, as well as designing the data collection strategy for the samples weathered outdoors. The other folks that I listed on a previous slide have been involved as well on the testing equipment, creating and building the testing, designing and building the testing equipment, setting up the testing equipment, and developing the procedures. The sixth and final phase is deploying the solution. And again, this is one where this particular project may deviate from applying statistical engineering in a typical industrial setting, because the deployment of the solution for this project meant disseminating our research results in the way of technology transfer. So finding commercially, transferring the ability to produce testing equipment and make it commercially available, getting adoption of testing procedures being developed into standards, as well as the accompanying these adoption of testing procedure and standards is the publication of research results and presentation of research results like this presentation. As I said, now Geoff mentioned being bad at PowerPoint designs or PowerPoint drawings. So you can see from this drawing that I'm actually worse than Geoff at creating PowerPoint drawings. But what I'm emphasizing, or something that sticks in my mind about the phases of statistical engineering, is that rarely will you only have one pass through the phases, especially the last three phases. And that's obvious to me, or that seems natural to me because of the work on this project. Because in fact, the very first iteration of this project that I was a part of, we were not even actually able to carry through the entire strategy that we had set out. And we have iterated from strategy to tactics to deployed solution. I'm working on my 4th iteration at this point. I know Chris and Jim have worked on more before that. And so I'm going to spend the rest of my time talking about 3 of the iterations that I have worked on. The first one, and by iterations, I should say that I'm separating out iterations of the project by material. So we've worked with a material, finished with that material, looped back to strategy, and started again with a different material. The first material that I was involved with was one called Sealant C. This is a sealant material, obviously. It was not produced for commercial use, but instead specifically for this project, and it was designed to fail in a reasonable amount of time. Unfortunately, on the solar sphere, it did degrade in a reasonable amount of time. Remember, that's an accelerated degradation environment. However, sitting outside on the NIST campus in Gaithersburg, Maryland, it did not degrade over multiple years at all. So we couldn't even, for this first iteration, this first material that I took part in working on, we were not even able to complete the entire strategy, which was compare the predictions that we had made based on the data we collected on the solar sphere to the outdoor data, because the outdoor data hadn't degraded at all yet. The outdoor samples hadn't degraded at all yet. However, I will say that there were some, we were able to move to the 6th phase, which is deployment of solutions, because during the exercise, there was considerable progress made on development of outdoor testing equipment as well as testing procedures, and those were transferred to industry. The second iteration that I was part of was another sealant named Kraton. Again, not a commercially available material, but specifically formulated for the project. In this iteration, we made a tweak to the tactics, not the strategy. We were still focusing on the same strategy, which is the strategy I put up a few slides back, but we made change the tactic. Instead of weathering the samples at the NIST campus in Gaithersburg, we started weathering them in Florida, which has a much hotter and more humid climate than Maryland. There was more progress made on test methods and equipment, and on this iteration, we were able to completely carry through the strategy, comparing predictions of what we were going to see outdoors to what we actually saw outdoors. And I'll talk about those results in the next 2 slides. First, as Geoff said, data is key, and I could not in good conscience give an entire presentation without showing some data. So here is my first slide with some actual data on it. This is the data from the laboratory experiment with the Kraton sealant. There's a lot of information in this graphic, and I'm not going to dwell on it too long, but I'm going to point out some things that you would expect to see and that we actually did see. First, at low temperatures and low mechanical strains, remember, mechanical strain is the amount of either tension, how much we pull on the sealant, or compression, how much we push the sample and compress it. At low temperatures and low mechanical strains, the sealant degrades very little. You can see this in the upper left-hand panels because the points follow the horizontal dashed line at 1 very closely. 1 means that very little degradation was observed. At high temperatures and high mechanical strains, this would be in the bottom right-hand side of the graphic, you can see that the sealant degrades very quickly because the points decrease to 0 very quickly. So here is a comparison. Here is a comparison of the outdoor predictions for the Kraton sealant to what was actually observed outdoors. So I didn't describe the axes on the last plot, so I'll fix that, and I'll describe the axes on this plot since they're the same as the previous plot. The vertical axis on this plot represents degradation, a particular metric for degradation, and the horizontal axis is time. The points are the measures of outdoor degradation, the measurements of degradation on samples weathered outdoors. The solid line is our prediction of that, and the dashed lines are a prediction interval. So the predictions match what was seen outdoors pretty well. However, there's a catch, because to get that level of matching, there had to be a calibration. We had to do a calibration of 1 hour of weathering on the sphere equals X number of hours of weathering outdoors. Now, generally, this would be okay, except it was unfortunate that that calibration did not hold over time. So what do I mean by that? What I mean is weathering, the calibration was not the same when we weathered samples in the summer of 2015 as it was in the summer of 2016. We couldn't use the same calibration. So while we can see some success, it was not a complete success for this iteration of the project. Moving on to the third iteration in a different material, polyethylene, which is a plastic. I've said multiple times already, one use of polyethylene is trash bags. There are many, many others. And one tweak we made in this iteration, we made another tweak to the tactics. Again, not the strategy, same strategy, but we made the tweak we made for the tactics was to measure UV exposure both on the sphere, which was done anyway, but also measuring as best we could UV exposure on the samples that were weathered outdoors. And the thought was that this would remove the need to calibrate, that the calibration factor had to do with UV exposure, in that UV exposure on the sphere was much more intense than UV exposure outdoors. So again, showing some data. Here is the laboratory data for the polyethylene experiment. In this case, as opposed to varying two weathering factors, only one weathering factor was varied, and that was temperature. From 30, you can see as we go from 30 degrees Celsius to 50 degrees Celsius, the degradation rate is accelerated because the curves decrease to zero more quickly. And this is perhaps one of my favorite graphics that I've made of all time. So again, in this graphic, the vertical axis represents degradation. The horizontal axis, again, is time, not UV. We're using UV exposure as a surrogate for time, and here we've used time for prediction, because that is eventually how we want to predict degradation. The points are measured degradation outdoors. The red line the red curve is predicted degradation. The band is a prediction interval. And what you can see, one of the reasons I like this graphic so much, is that about 1 month after the beginning of exposure, we are predicting essentially no degradation to complete failure, and we actually observe that in the field. So this graphic is one reason for polyethylene. I say that we have achieved complete success of doing this service life prediction. Now, for other materials, we have seen less success, even in other iterations that I haven't talked about. But for polyethylene, this has worked very, very well. So just in summary, I have talked about the 6 phases of statistical engineering using service life prediction as context for the discussion, emphasizing that the phases do not represent necessarily a linear progression of start to finish. I think that almost without failure, once you get to the phase 6 the first time, almost without failure, you're going to want to loop back to one of the other phases and move through again. And the natural phase to me to loop back to, it will typically be strategy. And if we have that concludes my presentation. If we have some time for questions, I will do my best to answer them.
Adam, I have a quick question. So applying the statistical engineering methodology, was that something that was accepted then by the team? Did you have any issues in convincing them?
So I will say, so this was more of a retroactive application of statistical engineering. I did not join the team initially, though I know that at least in some way, if not explicitly, all of the phases were carried out. It was not necessarily explicit. Let's see. Okay, so a question: does UV strength change depending on location? Meaning degradation may vary. Yes, that's a very good point. Yes, UV strength does change, of course. Farther south, you get more intense UV than farther north. But if we, so the hope is that measuring appropriately the amount of UV, the dose of UV, how much UV the sample is actually absorbing, that will account for those differences. We have not tested that at this point, but it's certainly a very good point. My collaborator Chris White has chimed in on chat that the work is well accepted by the entire team. So thank you very much, Chris. Freeze-thaw cycles. So that's a very good point. No, that has not been addressed by this research, but certainly that's a very good point, especially with sealant in buildings farther north you go, because in the summer they'll thaw out, and so they will actually experience a much different mechanical strain than well, at least in terms of mechanical strain, it is addressed by the prediction strategy, but we haven't tested on a location where you would actually experience that freeze-thaw cycle. We've only tested around the year, but in a place where it doesn't really freeze.
All right, thanks again, Adam. So I think now we'll transition to our third and final speaker, Jim Simpson. So Jim, I'll let you pull up your slides. Jim is a principal of JK Analytics, where he currently coaches and trains across various industries and organizations. Jim has served as an operations analyst for the Air Force, and he also was a full-time faculty member at the Air Force Academy and Florida State University. Jim has developed many courses on design of experiments and test science, and has personally taught over 200 short courses. And a lot of the material that he's developed has been formally adopted by the Department of Defense Acquisition University. So Jim, I will give you control.
Thank you, Rebecca. Hopefully you can hear me all right and can see my screen. And
yeah, we can hear you good.
Okay, great. Thank you, Adam. Thank you, Geoff, for your introductory comments. I think this will segue nicely into maybe another way to look at our types of problems that we have in statistical engineering. This is focusing on DoD, at least right now, but it's a general problem that we're facing in the Department of Defense, where we have autonomous systems, or we have systems that are being conceived and built and produced that have some degree of autonomy to them. So what do we mean by that? A lot of different definitions out there, and not sure everybody agrees, but essentially, we're talking about the freedom to select a course of action, as you see there in the first bullet, to achieve higher authority objective. I have Ham the chimp there from 1961 going off into space. I guess maybe this was before or after, I don't remember, but you know, and so it's really thinking about a system in terms of the human component, the machine component, and in the case of Ham, it's a human animal machine components, right? But the idea is that we want to have a capability that's delegated to the machine that enables the human machine system to do their mission. So one way to think about it, and any sort of analogy or any sort of system will fall apart to some degree when we talk about examples. But if you think about the drones that are out there, the UAVs that are out there, there's some degree of autonomy that's going on, even though piloted to a large extent. So if we think about autonomy in systems and primarily for the military, what are some of the aspects to a test and evaluation of them that we need to focus on if we're going to apply the scientific method, if we're going to apply design of experiments to some extent in test and evaluation? And you see the list there of 5 different attributes. One is that the factors and variables, the levels, can get out of control in a hurry. And so it's just a moving target in terms of what those factors and factor levels are, as well as this surface that we would ultimately be fitting using some sort of statistical model isn't smooth at all, and could have not just hills and valleys, but discontinuities. So what are the best methods for analysis, let alone experimental design? There's issues with transparency. We have trouble with cause and effect, particularly when we have artificial intelligence involved and we have emerging behavior involved, as you see with that last one, that we're really not at any sort of stable point at any particular time, and we're continually changing. So simple problem, as you can see, and we should have all the solutions at our disposal. So this is a little different from what Adam was talking about, in the sense that I think we're at the beginning of trying to tackle this type of problem, and we really don't have a whole lot of answers, and we have a lot of challenges, as you'll see in my concluding slides. So we'll discuss some of those. Just a picture here of the scientific method in terms of how we apply it generally for design of experiments. And you can see that one of the natures here in plan, design, execute, analyze is that it's iterative and cyclical, which we will address upcoming. So there's 2 aspects of autonomous systems that I want to focus on in this talk. One is that we need to come up with an approach that generally is sequential, particularly with autonomous systems, because they're so dynamic. And we'll talk about some of the specifics associated with that and maybe some ways forward. The other thing we want to talk about is that in DoD acquisition, it's become the standard now that we have a simulation of whatever it's a system we're trying to acquire that goes right along with the real system, or even a production representative or prototype. So the simulation becomes the artifact that we lean on quite heavily, both at the component level all the way up to the system level, to be able to learn about whether or not the system is going to be able to deliver. So in modeling the simulation, we want, and Geoff mentioned this a little bit earlier, we want to be able to make sure that that simulation is valid. And so what are some methods for doing that, particularly in face of autonomous systems? So do we test? And in the military, we do almost continually. This is an attempt to show that plan, design, execute, analyze cycle in several different contexts. One context is to think about it at the subsystem level. So if I have air-to-air missile, for instance, or air-to-ground missiles, we're going to be using as examples. Well, I've got fins on that missile. Maybe it's just the fins themselves that I want to study in terms of their aerodynamic behavior and their ability to affect the movement of the missile. So forces and moments. So maybe I'll look at things at subsystem level, maybe at the system level, and then integration of the system into a larger weapon system. So that's the vertical part of this slide. The horizontal is to say that we're going to be doing some testing early on in development, and then all the way just prior to making what we call the fielding decision and operational test. And so we'll have to develop plans for those tests, execute those tests, and then hopefully learn from those tests as well. Modeling and simulation, big role, as we talked about earlier, and not just at particular entry points into the acquisition cycle, but all throughout. And it has become the reality that even though we build these systems, the actual systems, and evaluate them through test and evaluation, there are a lot of different ways that we can't actually test them because due to risk and safety, and we just don't have the assets and so on and so forth. So the simulation ends up pulling the lion's share of the load when we do those kinds of things. All right, slide, there we go. One particular example. So this is an HH-60 aircraft that all three of the services use, various different missions that they use them for. But something in common across them is that they need to be able to hold and hover, maintain a particular location above ground in various different environments. And you're seeing there in the two pictures, sort of that brownout type of situation in the desert. You see what happens over water, and certainly over snow, you have the same kind of situations do over in the desert. So lots of times the pilot just has to depend upon the algorithms that are in the aircraft and software, a bit of autonomy there for the machine to be affected by the algorithms. And so we need to be able to test and evaluate that type of behavior. And if we're just focusing on the automated hold and hover aspect, we can think of maybe factors and levels for that particular system. And you see there that largely these factors are environmental in nature. And so it's not really buttons on in the cockpit. It's not necessarily the way we configure the software. It's just, let's go and test this thing in various different conditions. And so how do we go about doing that, particularly considering the risks and the safety and the autonomy that does take place? And what is the most efficient way to go about doing it? So you see here about half a dozen or so factors and upwards of 5, 6 levels of different factors. Think about what the design would look like. Think about iteration in terms of a sequential approach and how we would best cycle through the analysis and then back into another design. So just for this particular example, what are some of the considerations? As I mentioned, the factors are mostly environmental. So if we focus on those, what other things should we be focusing on in regards to the software that is being developed, and how do we better vet the software? Factors certainly challenge the system under study. And what if we deviate from the conditions and so forth? So these kinds of things that come up actually prompt us in those last two bullets to be thinking about, one, a sequential nature in terms of the process that we go through, and then how do we use a simulation, either a digital simulation or a simulator where the pilot can go and safely crash in the simulator. How do we get those involved in terms of testing so that we can learn the most in a very efficient manner? So if we think about sequential, Geoff mentioned George Boxton. Every time he starts off, he was thinking about this sort of deduction and induction iterative process, and we thank him for that. And so what we would like to do is to integrate that kind of thinking in the way we do our testing, the way we do the analysis. And really, this is a statistical engineering through and through type of effort, because we don't have a lot of solutions to just pull from a toolkit on in order to do this. So just a couple of thoughts that we're going to be sharing here along the way. But one thing to be thinking about is in autonomy, we've got sequential test design, but almost on the fly when we're testing, that test design may need to be modified. And how do we go about modifying it? Certainly in autonomy, we're going to have quite a few observational variables that we're just collecting or observing, and those may be very, very dynamic as well. And then the analysis should be near real time as well and allow us to be iterative. I think that's just encouraging, again, this cycle, and the 3 arrows on each is to say we're just going to go round and round and round and keep learning. Now, from an experimental design structure perspective, we know about a lot of designs, but essentially we need to be moving left to right up at the top there, from fractionals to fulls to some sort of response surface to something even more complex than that, and building upon the knowledge as we go. And then what you see down there at the bottom row as we're moving across is, well, what happens when we add factors and add covariates or recorded variables and change levels along the way. How do we best do that so that we can corporately learn, such that we can learn, the sequential idea is that we're building knowledge. And here we're changing things to the point where do we have to start, when do we restart, perhaps along the way. All right, so that's a little bit on sequential. Also wanted to be thinking about the modeling and simulation world. And this is borrowed from Rebecca's team up at IDA. And actually Laura Freeman came up with this a few years back, which is on the left-hand side of that diagram, it shows where the blue dots we're doing in simulation and doing more testing, and the white dots are the live testing that we go and do. Can't do as many, but it covers the space quite nicely across the difficulty of the mission and the environment. But that's not always easy to do, and it's not always practical, and it's not always the case. So what ends up happening quite often is that the testing that we do live is constrained to a very small part of the full envelope, what we call the operational envelope. So we're leaning on simulation to answer a lot of questions, and so that simulation needs to be valid. Another example, so hold and hover system. This is actually systems that are being brought together, and here I'm showing you. Well, first of all, let's talk about the weapon systems. So, Joint Airstrike Standoff Missile is a big weapon that is air to ground, and then SDB-2 is a smaller weapon that is air to ground. It's a glide weapon with tremendous sensing capability, and the MALD is just an air decoy. But think about deploying all those simultaneously from multiple aircraft, and then having those weapons talk to each other. They're going to communicate. They're going to real-time pick out targets that otherwise were not identified until they were out to see them, and then they were going to organize themselves in a fashion to kill the most targets on the ground. So quite a bit of autonomy going on there. How do we test that type of situation? Just pick one, pick SDB-2, and that's just a single weapon system, but we're going to deploy multiple ones of those, and we're going to see how SDB-2s can talk to one another, have some freedom to talk to one another, and this is going to be human-machine teaming, right? So there's going to be a lot of safety stops in there as well, to make sure that nothing, really bad happens. And this is a challenging project. Well, first of all, they're going to figure out how to do some of this kind of thing in a simulation. So that's what I'm picturing over there on the left-hand side, sort of a complex slide here, but left-hand side is building a simulation. The right-hand side with the pictures are the live testing that we do. And in validation, we want to bring the two together. You see V and V down there in the red circle. at the bottom, we're trying to bring the live testing together with the simulation to validate that simulation. We also obviously want to learn from the live testing as well. So how do we design the tests for the live? At the component level, we like to think about it as a tiered levels for the live, the component level, the subsystem, and then the all around or end-to-end full system testing. And then how do we feed that to the simulation? Well, one way to think about it from a systems engineering perspective is that we'd like to populate our knowledge about validation by taking advantage of planning good live testing at those 3 tiers that you see over there on the right, and then using that information to validate the sim at a model level. Different capabilities you can see M1 through M6 there for the simulation, and then subsystem level for the simulation, and all the way at the system level. And the system level is probably the easiest one to think about when it comes to applying experimental design. A whole bunch of factors, a whole bunch of performance measures, and we would then go through our process. But how do we do that with autonomous systems? How do we get our handle on something that changes so frequently? Just to reiterate the 4-step process yet again from a slightly different perspective, if we want to be thinking about adapting experimental design for autonomy, let's start with maybe checklists that we can go down through for each one of the steps and figure out how to modify it best for autonomy for both the sequential aspect and for simulation validation. Sequential and validation together here, actually not too bad on time, I think, in terms of finishing up. But this is sort of the get off the stage technique or method that we want to maybe throw out there for you to chew on. And this actually leans on work that Pete Parker and Rachel Silvestrini and Doug Montgomery did probably 15 years ago when they built these hybrid designs, which are great for computer experiment simulations. So the idea is that we have SF, which is the space fill initial portion of the experimental design, and augment the space fill with, say, I-optimal points where we're going more towards the edges and corners to be able to better model a response surface at the end of the day to better understand how factors affect responses in a simulation. And this is just showing some diagnostics at the bottom, how that improves when we augment. So that could be something that we would do, and I'll show you what yet another augmentation that we would do in a simulation experiment. But in validation, what we would do is run those points in the simulation, and then hopefully run those points as well if it's a nice efficient design and affordable and live, and compare the response surfaces. That's what we are doing here, sort of an eye chart, but compare the response surfaces coming out of the live testing, what we say test data there, to the simulation output, and see if we get essentially the same kinds of results. Excellent protocol for validating a simulation. It would be nice if they matched as well as these two here, which, as you can see, probably some made-up data. One thing else maybe we could do is if we take that hybrid design, we could maybe add runs or points to it. So the hybrid design here in 2-space is a lot more points than we showed you a couple of slides ago. So all these little dots are points, and then the red densities here are showing that we have the I-optimal points as well. So a whole bunch of points, and then maybe augment this after we analyze the points and see that maybe there's some contours in terms of performance where you can see in this the orange triangle, that we have some either better performance or worse performance than anticipated. And so we want to study that region of the factor space a little bit more and better understand it, add some more runs to our simulation model, whether this is for validation or whether this is for learning and characterization, but it's the idea of a sequential approach. So what we're seeing down here, bottom left, is the additional points that we add. And then in the graphic to its right, we're seeing what the combined set of points looks like. And the idea in this series of experiments is to learn overall and learn well. And then by augmentation and adding points, we can learn even more about particular regions of the factor space to get us to the point where we can estimate with good precision, well understand the input-output relationship. So lots to maybe ponder and just scratching the surface in regards to these types of problems. And as you can see, what we're doing is applying experimental design techniques where we're autonomy being the challenge, not necessarily straightforward. What these two slides provide, and I think the slides are available for everyone, is, let's take a look at sequential. What is the benefit in autonomous systems? Well, we can adapt, and we know that that we've got a very dynamic type of environment. So if we go with sequential, it has a benefit to it. But the C's there are challenges, and this is just a small list of, well, how do we take a sequential approach and really make it functional and feasible for autonomous systems? Likewise, when we're looking at validating a simulation that needs to be, I would suggest that with autonomous systems, we're going to need simulation to answer even more questions than we normally would prior to going to live. So that simulation needs to be valid. Some benefits to the approaches that we do have there, but then a lot of other unanswered questions. So what I'm saying down at the bottom, what I'm encouraging, and what a perfect audience that we have here is, hey, let's go and go forth and conquer some of this via some research, via trying to find some simple example and latch onto it. If you got one of those remotely piloted drones, quadcopters, whatever they're called, and you can set it on autopilot and go mode, maybe that would be a good project to use, and then see about trying different strategies and see what would work. And I think I've exhausted the time and certainly enjoyed it. And if you have any questions, happy to answer.
Thanks a lot, Jim. Yeah, I think we can take time for a few questions. I'll go ahead with the first one that I received. Can you talk a little bit about problem definition? Is that something that we need to revisit often as we learn more during sequential data collection? And can you get agreement from all of the stakeholders?
You had to start with a softball, didn't you?
Well, you can blame Christine Anderson-Cook.
Yeah, so problem definition, that's usually thought of as something that we work hard on right up front, and then that's settled and never have to revisit it. But absolutely, Christine, this would be something that you would want to have as part of your iterative loop, and getting all team buy-in. So obviously we would need to form a core team that has got essential stakeholders in it from all the important representative areas, and make sure they're on speed dial so that we can keep revisiting problem definition and scope. Absolutely.
Was the autonomy software learning during the experiment?
Generally they are. And so if it is learning, right, then we've got this, what we call emergent behavior. And as a result, you'd have to have some controls in place during the testing so that they're not learning and then changing behavior. So maybe learning and storing that for future tests. So great question.
Do you think the DoD currently has the in-house expertise in statistical engineering to conduct the sort of uncertainty-heavy analysis required for autonomous systems? Do you think we need a specially trained cadre of autonomous T&E pros?
We do need a specially trained group of autonomy T&E pros. Very, very clear. We had a workshop back in 2019, October. So that's half a year ago or so, a little past. And we have a handful of people that are really experts on the autonomy side. And good news is we have a pretty sizable group of statistical engineers that are interested in working the problem. But, you know, DoD is enormous, right? And if you just talk about one service, they need help. So, yeah, if you're interested, send resumes in to the DoD and see if you can get yourself hired on. Any other, which ones should I go after here? We've got quite a few.
Oh, how about we address the question that just came in, the one from John Heeman. If I have two drone systems, one is autonomous and the other is human controlled, do I need a different DOE analysis for these experiments? Yeah,
so good question. So I think one of the biggest challenges in designing this is first is what are we going to allow in terms of the human controlled versus autonomy in terms of their sharing. And that is actually an area that they've made some headway on. And the term escapes me right now, but I've made some headway on in terms of trying to get that software into the test and evaluation environment. But like you just said, I think in terms of, I would suggest that would be different DOEs for each. And then what you need to do is figure out a way to bring those DOEs together, right? Because they're going to be functioning simultaneously. Bring them together as one matrix so that it can be, you know, row one can be executed. And you'd be having both the machines having their own factors. That's a research area too. That's something that we've gotten into with System of Systems, DOE. That's your classic. We've got system 1, 2, 3, 4, 5. Each one has its own DOE, and then we got to bring it together for them to be tested together.
So, all right, I think with that, we'll look to wrap things up. Thanks, Jim, for a great talk. Thanks to all of our speakers for today's session on statistical engineering. If you'd like to learn more about statistical engineering, as Geoff mentioned, there's a website. It's ISEA.change.org. So I encourage you to check that out. There's a lot of great material there. So thanks again, everybody, for coming today.